thanks for watching, and here is a really cool property of the Fourier transform that proves to be useful in practice. Because the question is, what happens to the Fourier transform when you shift a function? In other words, what is the Fourier transform of not f of x, but f of x minus a? So in other words, if you shift f to the right by a units, what happens to the Fourier transform? And the answer is very cool, namely an extra exponential factor comes out. So in other words, if you do f of x minus a, and you take the Fourier transform of that, then you get this extra e to the I kappa a factor that comes out. And then f hat of kappa if you want. Now, more precisely what this means is that if you define g of x as the shifted function, then the Fourier transform of g is e of I kappa a times the Fourier transform of f. And you can prove this, and in fact we do it on the homework where you just write the definition of g hat and use a little u sub. And today I just want to give you two quick examples of this. So the first example is find the Fourier transform of e of minus x minus 4 squared. Which, notice, is the Fourier transform of a shifted Gaussian. So let's start with the fact that the unshifted version, so e of minus x squared, it's square root of pi, I believe, e of minus kappa squared over 4. And what this is a shifted version by 4 units. So by a equals 4 units. And so the Fourier transform of minus x minus 4 squared hat, once again, it's e, I believe, ei kappa a, so ei kappa to the 4th times the unshifted version, so e of minus x squared hat, so just e 4 kappa I, and then square root of pi, e of minus kappa squared over 4. So you see, if you know the Fourier transform of the unshifted function, you can easily also find the Fourier transform of the shifted function. And I wouldn't be surprised if this has some cool application in terms of signal processing, because I kind of interpret this extra factor as going to another level of the spectrum, because the spectrum, I believe, behaves like complex exponentials. All right, and of course we can also do that in reverse. So in this case, find a function whose Fourier transform is the following. So I believe e of 2 kappa I and an e of minus 3 kappa squared. So in other words, we want to write this as a hat. And in this case, because we have this e2 kappa I, it's signal shifting. And so let's first start with this function. So start with the unshifted version. e of minus 3 kappa squared. And in a previous video, we actually wrote this as a Fourier transform. So we found that the answer was 1 over square root of 2 pi e of minus x squared over 12 hat. And this is the unshifted version. And now simply, if you add this complex exponential term, you shift it. So e of 2 kappa I, e of minus 3 kappa squared. Well, that is e of 2 kappa I, and then 1 over square root of 12 pi, and e of minus x squared over 12 hat. And remember, this factor just shifts things. So we get 1 over square root of 12 pi, and then e of minus x minus 2 squared hat. Squared and then hat. So what is our answer in this case? It's just the shifted function. So once again, this function is the Fourier transform of 1 over square root of 12 pi, and then e of minus x minus 2 squared. And I do just want to mention two things. First of all, you have seen this before in the Laplace transform, where we had, for instance, e of minus 3s, and then Laplace transform of t, let's say t squared, and what this did is just shifted and jumped. So t, I think minus 3 squared, u3 of t. So this is just a Fourier transform analog of that. And most importantly, why is that useful? So there's two really cool applications. First of all, and you will do that on your homework, you can use the shifting property to solve this transport equation. And you can also use this shifting property to solve the wave equation, both using the Fourier transform. So really powerful stuff. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.